Yes. Hello, I'm James Ingram for AutoControls-dot-org. The title of this video is DCC-Brake-On-Analog-DC. Now what does that mean, DCC-Brake-On-Analog-DC? It comes from the NMRA recommended practice 9.2.4, and paraphrasing that I'll read: the National Model Railroading Association, NMRA, RP 9.2.4 says a DCC engine running on normal DCC track power upon encountering reverse polarity DC will slow to a stop with normal deacceleration. When DCC power is restored, that train will then begin accelerating with its normal acceleration settings. This is sometimes implemented for reverse DC only, often for either direction DC. It's probably best if it stops on both directions of DC current when it's introduced. Now you might ask, who cares about this recommended practice? Most people probably don't. It was apparently put in by the NMRA to prevent runaway trains, like if somebody accidentally got DC power on a layout that's supposed to be DCC, so all the engines wouldn't start running at once and you'd have a lot of runaway trains. But it also works handy for people trying to do automatic controls. This is probably most commonly used by the devices known as DCC-Bitswitch. You might ask, what are my qualifications to do this video? Well, I probably know just enough DCC to be dangerous, but with the help of Fred Cupp, my local technical consultant and helper and repair person, who actually does all the hard work, to be honest, Fred Hughes of DCC-Bitswitch, and Bob Brashear, who's kind of an LGB DCC guru, I'm going to hopefully manage to blunder my way through this video. Here's the actual page from the DCC-Bitswitch installation manual. He says, test your engine decoder settings for proper braking operation by connecting a length of test track to the CD output of the brake signal generator. With the brake signal generator, set the manual, start the engines moving. As the engine moves, switch the brake signal generator to auto. The engine should slow to a stop. When we change it from auto, we're suddenly changing from DCC on the rails to DC on the rails. Then he says, switch to manual, the engine should resume. So when we switch the lever on the DC brake generator unit, when we switch it to manual, that starts sending DCC out to the rails again, so the engine should start up again. Let's take a look at the paperwork for the same arrangement. Here's our command station, our DC signal coming into the brake generator, and here's our four terminals. Again, on terminals A and B, we've got DCC going out to the track. When this is in the automatic mode, which is where you'd probably normally run it, this switch is thrown out toward the track and it sends a DC signal out to the track. Now this is normal operation. Again, the bit switch which would be right in here. And again, let me emphasize, there is no bit switch in this video. We're not demonstrating the bit switch, just the stop on analog DC feature. But if there was a bit switch in here, that picks up the DC or DCC signal, whichever one it needs to send to the track. Now here we are with almost the same drawing, but now we've got this switch shown in the manual mode. Everything's the same on terminals A and B, DCC still going out, but what's different, now we're using that, now we're bypassing the rectifier and just sending DCC out to the track. So you can see no matter which of the two sets of input wires the bit switch picks up, it's sending DCC to the track. So this means if a person's, again, this is manual control, so if a person's driving the train around the layout, when it goes through a bit switch, it doesn't matter what position the bit switch is in because it's always putting DCC to the track. It essentially makes the bit switch control system totally invisible, and it doesn't do anything. Now here's a third version of this drawing showing how we're going to do it for our test. We've got the DCC coming into the brake generator as always. We're going to start with this lever on the brake generator in the manual position. So when we start the train up, it'll be sending DCC to the track. Now when the train gets up to speed, we'll flip this lever from this position away from the track. We'll flip it over toward the track, which will change it from the manual position to the automatic position, which will change it from DCC to DC current. So suddenly we're going to be switching the track from DCC to DC. We're basically simulating what happens when a DCC bit switch starts braking a locomotive by changing from DCC to DC, except we had no bit switch here. We're basically simulating it by using this brake, by using the lever on this DC brake signal generator. Here's our test setup. We start with an NCE power cab, which is essentially a command station built right into a control head. Over here is the power panel, which is really part of the power cab, but basically just where all the wires connect. We go out to a DCC-Bitswitch DC brake signal generator, and over there and then on to a terminal block and out to the test tracks. Let's take a closer look at this DC brake signal generator unit. Basically, we've got a full bridge rectifier here to rectify DCC to DC, capacitor to smooth out that DC signal, and there's a switch to switch the output on terminals C and D. Now going back a little bit, we have coming into the unit is DCC coming from here, the command station. So this is the input to the unit, two terminals carrying normal DCC current. On the A and B terminals, these would go to a DCC bit switch unit if there were one. Remember, this is a test video. We're not actually demonstrating the DCC bit switch. We're just demonstrating the stop on analog DC capability. So we're not using these two terminals for this test video, but these would normally go to the DCC bit switch unit and power the DCC bit switch unit and also go to the track. Now on terminals C and D, when this switch is in the automatic mode where it is now out toward the track, the DC signal coming in is rectified to DC and goes out on these two terminals. So the DCC bit switch unit, which would be here in the chain of units, if it were here, that changes what's going to the track from DCC to DC depending on which of these two terminals it picks up. All four of these wires go to the DCC bit switch unit, and the DCC bit switch unit sends the appropriate signal to the track, either DCC or DC. Now when this switch is pulled back into what they call the manual mode back here, it sends DCC out in these two wires also. So that's so a person can override the DCC bit switch controls and there's DCC going to the track in all cases, because when all 4 wires are carrying DCC, then regardless of which way the bit switch changes, the track is out here is still getting DCC current. What we're going to do is start this engine up, and when it'll be running under DCC power, and when it comes around the track and gets to where this piece of red cardboard is, just about where it changes from curved to straight, I'll switch the brake generator from manual to automatic, which will change the track current from DCC to DC all of a sudden, and this engine should start slowing down under its normal deacceleration momentum. Here's a drawing taken from the block control part of the DCC-Bitswitch website, and you can see where I've shown it in pink is the part he shows as the brake section. So the DC would be put to the part in pink only, but the rest of the loop here that's not in pink, that would be DCC current all the time. So to make an actual system with multiple trains, you need a much bigger loop than what I've got on my little test layout here. The locomotive's parked back by that red piece of cardboard. I'm going to start it up to speed step 28, which is the maximum. You probably wouldn't normally run this fast, but just to illustrate the Brake-On-Analog-DC principle, I'm going to run them at maximum speed. And when it gets around to the red cardboard, I'll throw this switch here, which will change the track power from DCC to DC. Okay, right about now, and you can see that locomotive drifted to a stop. It's under CV3, CV4 equals 2, I think, 1, excuse me. That's the deacceleration variable. It's set for maximum deacceleration. And it's going to wait there while the track power is set to DC until we switch the track power back to DCC, which I'll do right now. So switching it back to DCC, it starts back up under its normal momentum. Now I'm going to run the same test again, except I'm going to change the momentum on this engine. The momentum was set to 1. I'm going to set it to 3, so I'm going to push the momentum button and enter a value of 3 by pushing the 3 key. So now that momentum should be set to 3, and the way I've got this cab configured, I modified it from the default setting, but a momentum of 3 sets a value of 3 in CV4, which is a deacceleration configuration variable, and it sets a value of 6, twice that amount, in CV3, which is a configuration variable for acceleration. And the bigger you make this number, the longer the train takes to accelerate or deaccelerate, i.e., saying it another way, the bigger you make that number, the more momentum the train has. A value of 0 is what they call direct drive, where there is no momentum. So 1 is the minimum amount of momentum which we had for the last test. Now we've got the deacceleration momentum up to 3 and the acceleration momentum up to 6. Okay, here we go, same test but more momentum. Increase to speed step 28. You can see the locomotive takes a little bit longer to get started. And get ready to throw the switch when it reaches the red cardboard. You can see we've got more drift. You may also notice the headlight goes off on this engine. Most of the engines, the headlights stay on. This is an older Digitrax decoder, and for some reason the headlight won't stay on. Now we have a different locomotive, still HO scale, with a QSI quantum sound decoder in it. The deacceleration momentum configuration variable 4 is set to 1 on this locomotive, but it still takes a fairly long time to deaccelerate. It seems like each of the different brands of decoders have their own characteristics to some extent. So now we'll start this one up and do the same test. Going out to a maximum speed of 28. When it gets to the red cardboard, throw the switch. You can see that engine slows to a stop. You still have the headlights and the sound even though the engine stopped. And again, that engine will sit there and wait until we switch the track power from DC back to the normal DCC, which I'll do now. So here's the switch back to DCC. And you can see the engine starts up under its normal momentum and goes back to whatever speed it was set to. We've now got an S-gauge engine on the track. We'll do the same thing we did with those two HO engines. We'll accelerate it up to maximum speed step. That's step 28 using DCC power. And when it gets to that piece of red cardboard, I'll use the DCC-Bitswitch brake generator to switch the track current from DCC to DC, and it should slow down. Okay, we're almost to the cardboard. And you can see the engine deaccelerated under its normal momentum, and you can see we've still got the sound and the headlight and the flashing light on top of the cab. Now I'll switch the track power back to DCC and the engine will accelerate under its normal momentum. Now we'll do the same thing in reverse. We'll run up the maximum speed step 28 in reverse under DCC power, and then at the same point when the engine gets to that red cardboard, I'll switch it to DC power and it should slow down to a stop. And you can see the train again came to a stop, and we've got a decoder. Fred Cupp put a decoder in that caboose that you might be able to see makes the rear lights flash. You can see we still get that feature on DC power. And again, when we switch it back to DCC, it'll accelerate back in the direction it was going. Here's the other S-gauge locomotive, the same Soundtrax Tsunami decoder in the engine, a little bit different engine sound and lighting effects. We'll do the same thing, run it up to speed step 28 and switch the track power from DC to DCC. Excuse me, from DCC to DC. And you can see, as before, it brings the train to a gradual stop. We still have our sound effects and still have our headlight and flashing ditch lights. Now I'll switch the track power from DC back to DCC, and the engine will start up with its normal momentum and resume traveling forward. In the locomotives we've run so far, they've all had configuration variable 29 set to no DC or analog off. Now, that means they're not supposed to run on DC. Now, this locomotive is configured for analog operation on, or saying another way, to run on DC. So, just for illustration, we'll run this locomotive up to full speed, and what will happen when I throw that switch to switch the track from DCC current to DC, it'll just keep right on going. So you can see it's slowed down a little bit, but it's still running, continuing on DC. So basically, you've got to make sure your locomotives are set up to stop on DC in order to use this type of a system where you're using DC analog current to stop the locomotive. And I haven't talked about that much. That's a big project sometimes, getting the locomotive correctly configured. It almost always involves setting CV29 to analog off, and for some other locomotive you have to set another couple variables sometimes. Now we're going to look at the large-scale loop for a second, and I've taken pains to ensure that on this large-scale loop I've got reverse polarity DC. So normally for the smaller gauges, like N gauge, HO, and S, in the direction of travel, the plus rail is the right rail. However, large scale is the opposite of the smaller gauges. In the direction of travel, normally the left rail, which would be this rail, is the plus rail. Since I want reverse polarity DC, I'm putting the plus on the right rail in the direction of travel. I can show that with a DC voltmeter. The more obvious way is just put an old analog engine on the track. This is an old engine with no decoder, so when I put it on this track with DCC current, it's going to just sit there and buzz. Now they tell me I shouldn't do this for more than a few seconds or it'll overheat and ruin the motor in the engine, but for a few seconds it won't hurt it. So I'm going to put it on the track, and it's just sitting there buzzing. Now as soon as I throw this switch to put reverse DC on the rails, you can see what happens. It takes off and away it goes in reverse. So that's an obvious way to demonstrate that there's reverse polarity DC on the rails. We've got an LGB engine back on the track there, equipped with a Zemo sound decoder. We'll do the same thing, run it around till it comes around the back curve, and when it hits the straight where that piece of red cardboard is, I'll throw this switch on the brake signal generator, which will switch the track current from DCC to DC. sound when it's laid on top of the cab. Now we'll switch the track current from DC back to DCC, and that engine will start up. Same test running in reverse. See, it stops on DC regardless of direction. It'll stop on either forward DC or reverse DC. Now I'll throw the switch to bring the track current back to DCC, and it'll start up and continue in reverse. Here's a USA Trains GP7 with dual motors. This engine also has a Zemo sound decoder in it, and this behaves very similarly to the black LGB diesel we demonstrated a minute ago. This will stop on both forward DC and reverse DC when you switch the track current to DC. So I'm going to start this engine up now and do the same test. Stop and idling on DC, still with the sound, still with the rooftop strobe. My headlights aren't working on this engine, but we would have lights if the lights were working. Now we'll switch back to DCC current, it'll start up. Now we'll do the same demonstration in reverse. When it gets over to the red cardboard, I'll change the track current to DC. Stop that DC current is forward with respect to the direction of the engine. So now we'll switch it back to DCC current. It'll continue the direction it was traveling in reverse. The large-scale engine that's on the track now is one of those very early LGB green diesels that came with the first multi-train system set. I believe this is one of the first engines LGB put a decoder in. I can't read any of the configuration variables or write any configuration variables, but this engine will stop on reverse DC. It will not stop on forward DC. I can't change the momentum, but it does have a little bit of momentum, so I believe it will work. It will stop when you change the track power from DCC to DC, and we'll demonstrate that right now. There's speed step 28, maximum speed. You can see when I changed it to DC, it in fact did drift to a stop. Now I'll change it back to DCC and it'll start up again. Now if we run this same test with the Loco going in the opposite direction, so now when DC is introduced its forward DC, what you'll see is this engine won't stop, it'll keep right on going. So when it gets to the red cardboard, I'm going to throw the switch. You can see now it's running on DC, but it doesn't stop, it keeps right on going. So bottom line, this engine will stop if you're running it with reverse DC when you introduce DC, but it won't stop if you have forward DC, so you have to get the polarity of the DC track current going in the proper direction. Incidentally, Bob Brasher tells me this green diesel might be possibly able to program the configuration variables by using an ancient method called register programming, which they used apparently a long time ago. But nobody around here at the moment knows how to do it, so we can't do this. But just for reference, it might be possible to program this engine if you knew the right methods to do so. This blue LGB steam engine that you see on the track is another one that came built in with a factory decoder installed. However, when you put reverse DC on the track like this test loop is doing, it just keeps right on going. If you run it backwards so that when you put DC on the track it's encountering forward DC, it in fact does stop after a while, but it takes a long time. So this engine probably would be very difficult to use on any kind of a DCC-Bitswitch type layout. If you had just this engine on a track by itself and you were trying to use a bit switch type system to put DC on the track to make it stop for like a station stop where it was the only train, you might be able to do it, but otherwise it'd be hard to work with. Now somebody maybe a lot smarter at programming decoders could get this to work better, but it's beyond my reach. I talked to Bob Brasher about this engine, and he said, if I recall from memory correctly, I think he said you had to go inside these engines and reverse the polarity to the wire, reverse the polarity go onto the motor to make them stop correctly. I tried reversing the polarity in software using the programming variable CV29 to reverse the direction. That doesn't help, but I'll go ahead and demonstrate this engine anyways just for reference. So switching to DC, it keeps right on going. I'll switch it back to DCC, stop it, reverse it, and speed it back up again. And again, I'll switch to DC by the cardboard. You can see it eventually stops, but it takes like half a loop to do it, and that's with CB4 set to 1, which is the maximum deacceleration. But if I switch it back to DCC current, it does start up and take off again. So it's not really usable for a multi-train system, I don't think, unless it can be better configured than what I've been able to do with it. Just a reminder that this little setup as you see it is just a test loop, because the brake signal generator is putting DC on the entire loop. On an actual railroad where we're using a bit switch to operate multiple trains, the DC part would just be put on one section. The only time you would use it like this if you had just one train on the layout, you were doing a station stop, then the entire loop could be changed to DC to stop the trains.